Hey everyone, let's take a look at number one in section 10.5. We're going to apply the ratio test to this series here. And just as a reminder, in the series summary sheet that I give you, the ratio test says to determine whether or not this series converges, we look at the limit as n goes to infinity of basically the ratio of successive terms as n goes to infinity. Take the absolute value of that ratio. And of course, this column remembers the column for convergence, first one here. So if this limit is less than one, then the series converges absolutely. If this limit is greater than one, then the series diverges. The one drawback, of course, is if this limit is one, then the test is inconclusive, and we would have to use some other test to determine the convergence or divergence of that series. So let's take a look at this. We will look at, of course, this is the A sub n right here. And so what I'm going to look at is the ratio of A sub n plus 1. So this right here, this portion right here is the A sub n plus 1. And all I'm doing is simply replacing n with n plus 1. All right. And then divided by A sub n, I'm going to just multiply by the reciprocal. So this right here is the reciprocal of A sub n, which is just the reciprocal of that. Okay, so now what do we do? First of all, we're taking the absolute value, but note for n going to infinity, all these values are positive, and so we can get rid of the absolute value bars. Now, if I multiply here, I get 3n plus 3. 3n plus 3 plus 2 is 3n plus 5. Okay, and then all I'm going to do is I'm sort of down here, when I multiply these fractions together, I multiply the numerators and I multiply the denominators. Well, I can multiply in any order, so I'm just going to sort of change the order that I multiply these denominators in. So the 3n plus 2 comes here, and this expression here comes over here. And the reason I want to do that now, you could expand all this out and, FOIL this out and then, expand and multiply all this out. But in this form, notice the limit as n goes to infinity. The limit of a product is equal to the product of the limits, provided these limits exist. And look at this first one. I hope you all can see that that limit is going to be 1, right? That limit's going to be 1. And you can use L'Hopital's rule one time, right? And because it's infinity over infinity as n goes to infinity. And the derivative of the top is 3, derivative of the bottom is 3. So the limit as n goes to infinity of this expression by L'Hopital's rule is the limit as n goes to infinity of 3 divided by 3, which is equal to 1. Again, you can see the degree of the numerator and denominator is the same. And so basically for large values of n, this is what you're looking at, and this simplifies to 1. Basically the same argument here. I'm not going to expand this out down here, but if I do, notice my highest degree term will be 5 times n cubed, right? When I cube n plus 1, n cubed would be the highest degree term there. And then so you can either use L'Hopital's rule repeatedly or just realize, right, you can divide numerator and denominator by n cubed after you expand down here, and you will get a limit of 1. So I hope we've talked enough about this in class that that should be evident. Okay, but both limits exist, and of course they're both 1, and 1 times 1 is 1, so that's the limit. So what does that mean? Remember what we said about the ratio test. If this limit is 1, then the ratio test is inconclusive. And in this problem, that's what they want you to do, to use the ratio test to either show the series converges or diverges, or state that the ratio test is inconclusive. And so this is what we would state in this particular problem. To actually determine the convergence or divergence of this, we'd have to use a different test. Okay, I hope this is helpful.